Greetings. Welcome to our review of 115A. I am Behzad Razavi. Today we will talk about bipolar transistors and their physics and their models, and then we will look at amplifiers that use bipolar transistors. And following that, we will repeat the same process for MOSFETs. So we'll look at the physics and the models of MOS transistors, and then amplifiers that use MOS transistors. As you have seen in 115A, there's a great deal of parallelism between these two. These devices act as voltage-controlled current sources, and then we build amplifiers using these devices, and the three amplifier topologies that you have seen in 115A are equally applicable to bipolar devices and MOS devices. Okay, so let's begin with MOS transistors. Let's begin with bipolar transistors, and just refresh our memory about their operation. So bipolar transistors, we saw that it's a simple structure consisting of two back-to-back diodes, so to speak. So we can construct it like this. We have three pieces of semiconductors attached to each other. For an NPN transistor, we have a structure consisting of an N plus region. So that's a highly doped N-type material. And then we go to a P material, and then we go to an N material. So that's an NPN transistor. And we said that the desired region of operation for this device is when the base emitter junction is forward biased. So current flows this way through junction, wants to flow this way, or electrons want to go this way, electrons want to go this way, holes want to go this way. So we want to forward bias the base emitter junction. So we say base emitter forward biased. So for example, we connect a battery here and connect the emitter to ground. So that provides some positive voltage across this diode and turns on the diode. Okay, now for the collector, meaning this terminal, we decided that we would like the collector base junction to be reverse biased. So because the base is sitting at some potential, for this junction to be reverse biased, the voltage at N has to be higher than the voltage at P. So we connect a voltage source here, and we call that VCE. And the second condition that we have is that the collector base junction is reverse biased. So these two together form what we call the forward active region. So these two constitute the forward active region. And this is really the only region in which bipolar transistors are used. If for example, the base emitter junction is not positively biased, not forward biased, then this junction is off, so that's not useful. And then if this junction between the collector and the base is not reverse biased and is forward biased, then the device goes into saturation, and saturation is generally undesirable for bipolar transistors. So that's why we insist on these two conditions to make sure the device is in the forward active region and provides the desirable properties in terms of amplification and gain and so on. Okay, all right, so that's what we obtain. In this region of operation, we can say that the collector current, meaning the current that flows this way here, let's change the color, this current, IC, is an exponential function of the base emitter voltage. So it's IS exp of VBE over VT. Vt is given by kT over Q. K is Boltzmann's constant, T is the ambient temperature or absolute temperature, and Q is the charge of an electron or a hole. But these are not easy to remember, so we just remember Vt itself. Vt itself is 26 millivolts, approximately at room temperature, so at 300 Kelvin. Okay? All right, so this says that the collector current is an exponential function of the base emitter voltage as long as these conditions hold. And that's great. It's a very strong device. With a small change in the base emitter voltage, we get a large change in the collector current. All right. But there is one more imperfection that the device has, and that imperfection is what we call the early effect. So the early effect arises because if we change the collector voltage, this equation says the collector current should not change because there's no VCE or VCB in this equation. But in reality, that's not true. As we change the collector voltage, it turns out that the effective base width changes, and as a result, the current changes. So we don't go through the details, we just accept the fact that if the collector voltage changes, the collector current changes by a small amount. Okay, that's called the Early effect. Someone named Early discovered this effect. Okay, so we have to modify this equation to reflect this phenomenon. And how do we do that? Well, we come up with a very simple modification. We say, okay, let's try to change that linearly as a function of the collector voltage or collector emitter voltage. So we take this whole expression here and simply multiply it by something that has the early voltage in it. So we say if the early voltage, the collector emitter voltage in it, let's see here, something that has the collector emitter voltage in it, because we are expecting that the current goes up as the collector emitter voltage goes up. Now we expect some dependence, and we're going to make it a very simple first order linear dependence. All right, well, so we just have to add some stuff here, because obviously if I just multiply VC by this, the dimension will be wrong. This has the dimension of current, this has no dimension, now this has the dimension of voltage, so that's not going to work. So we're going to divide that by some quantity to get rid of the dimension, and that quantity is called the early voltage. So VA goes in the denominator. Okay, but I still cannot multiply this by this directly, because that would indicate that if VC goes towards 0, this current has to go towards 0, which is not exactly correct in the forward active region. So I'm going to add another 1 plus here. So this is the overall expression for the collector current if the early effect is not neglected. And we use that for analyzing the behavior of a bipolar transistor in a relatively general case. Okay, so let's look and see if I have a bipolar device like this, and I simply connect a battery to, this is the symbol we saw for the NPN transistor. We have a VPE here. And what we see is that if I put this in a black box, like so, and I examine this current I see as a function of this voltage here, VCE. So we draw this as a circle to indicate that this is possibly variable. And we draw this as a battery, indicating that it's constant. So you might remember that if I plot this current IC as a function of this voltage, IC VCE, and if I am in the forward active region, and if I neglect the early effect, then IC is constant because VBE is constant. So in the forward active region, IC is constant. Okay? Now, if I include the early effect, I see some dependence upon VC. So as VC goes up, IC goes up. So the actual plot looks like this. All right? And this holds up to down to some value of VCE once we go into saturation, meaning once the collector voltage is less than the base voltage, we are in saturation, the device no longer behaves exactly like according to this equation. And at some point, it begins to fall. The collector current begins to fall, and we go down. So when the collector emitter voltage is equal to the base emitter voltage, we say we are beginning to enter saturation. So this region is called the saturation, and this region here is called the forward active region, or sometimes we just say active region. And in 99.99% of cases, we would like the bipolar device to operate here and not in saturation. Okay, so that's the basic model that we have for the bipolar device, this model. And this model is called the large signal model of the transistor. So we're going to say large signal model. So we have IC is equal to IS, X of VBE over VT, and then 1 plus a lambda, oh, no, sorry, that's for MOSFETs, VCE over VA. Okay? Now, what do we mean by large signal model? All it means is that this model is relatively general. So regardless of how much the currents and the voltages of the transistor are changing, let's say with the signal that's coming into the circuit, this model is valid, as long as we are in the forward active region. So that's why we say this is large signal, meaning VBE can change by as much as we want, VC can change by as much as we want. As long as we are in forward active region, this model is valid. Okay? That's just to emphasize that the levels of current and voltage changes are arbitrary. All right, so because the model is nonlinear, it becomes cumbersome in some calculations. So we've tried to create a linear version of this, which eventually translates to what we call the small signal model. But before we go there, let's just take a look at one interesting concept. So let me make sure that I covered everything I wanted to say so far. Okay, so this distinction between saturation and active can be visualized as follows. So I'm going to write visualization. So if we are in forward active region, we expect something like this. Okay, so the base emitter is always forward biased, that goes without saying. And the collector emitter is, the collector base is like this. Collector is higher than the base. So we say we are in forward active region. So we'll write here active. In our mind, nodes of a circuit or terminals of devices that are near top of the page are more positive than nodes that are near the bottom of the page. So we would think that this has a higher potential than this. All right. Now, as this voltage comes down or this voltage goes up, at some point they will be equal. And when this difference is 0, we say we are at the edge of active and saturation. So we are at the edge. And now if the collector voltage goes down or the base emitter goes up, we are forward biasing the base collector. So we draw it like this. We have some positive difference this way. The base is higher than the collector, and we say now the device is in saturation. Okay, so if you keep these pictures in mind and you look at the circuit and you're trying to find the voltages and so on, it becomes easier to keep track of things. All right, so these are all related to the large signal model and whether we are in the right region of operation or not. And now we want to introduce another concept that is extremely critical for any transistor, including bipolar and MOS devices. And that's the notion of transconductance. So let's change the color to, let's see, where are the colors? The colors are here. We go to this color. Okay, so we're going to talk about the notion of transconductance. Okay, suppose I have a bipolar device sitting here, and it's part of a circuit, and some signal is coming to the circuit. The signal comes here and changes the base voltage by some amount. So let's say we change this voltage by some delta V. You realize that signals are always quantities that are changing with time. So my voice, this video, all of these are quantities that are changing with time. So as we look at this base, it is possible that with time it changes by some amount delta V. So what I'm wondering is, how much change do I get in the collector current of this device? In other words, how strong is this device? How sensitive is this device? If for a change of voltage here, let's say 1 millivolt, I get 1 milliamp of current, I would think that device is probably pretty strong. If I get 1 microamp of change in the current, I would think that device is weak. Now, the notion of strong and weak has to be quantified, but intuitively we might expect that. So then I would like to see how much collector current change I get for a given change in the base emitter voltage. And this is just representing the reality in which the signals are coming into circuit and creating these changes. Okay, so that concept of strength of the device will be called the transconductance, and officially we'll define it as the change in the collector current with respect to the change in the base emitter voltage. And the unit is either 1/ohms. You can see that this is inverse of resistance, or sometimes be represented by capital S, which is Siemens. So it could be Siemens or it could be 1/ohm, whichever you want. So again, it's important to understand that transconductance simply represents how strong the device is, in that it generates a certain amount of current change in response to a certain amount of base emitter voltage change. So based on that, we can proceed and decide how strong the device is. Okay, so if I take the transconductance equation, if I take the current equation from here and take the derivative with respect to base emitter voltage, with respect to this guy, that's right, it doesn't have base emitter, what I will see is that GM actually happens to be IC over VT. So IC is what we call the bias current. We have taken a transistor, established the right voltages and currents in it, so it carries 1 milliamp of current, for example, and VT is known, 26 millivolts at room temperature. So this ratio gives us the strength of the device. This ratio says if we create some amount of change in voltage here, this change is GM times delta V. Delta I is GM times delta V. Okay, so now this naturally leads to the concept of small signal models and small signal operation. And the premise there is as follows. Here, we use this equation in the general case, whatever we want to do with the transistor, so long as we are in the forward active region. But there are some cases where we have a transistor sitting there, it has some static currents and voltages, and now a signal comes in, and the signal creates only small perturbations in these currents and voltages. Remember, the signal is a quantity that changes with time. So the currents and the voltage of the device will begin to change with time. But the changes are small. If they are, then we can resort to the small signal model and we won't have to deal with this nonlinear equation. So let's go to the next page and see how we will do that. So I'll add a page here. Okay, maybe one more page. Go back here, close this. Okay, so we're going to talk about small signal model. All right, so the small signal model is important when, say, if signals perturb the transistor currents and voltages by a small amount, small is somewhat poorly defined. We can replace the transistor with its small signal model. Okay? All right, so here's how it goes. I have my transistor looking like this. 3 terminals, base, collector, emitter. And if I know that I'm looking only at how the signal is changing the currents and the voltages, so I'm interested only in the changes in the currents and the voltages, I can replace this device as follows. Here's my base, here's my emitter, and here's my collector. So I will place a resistance of R pi between the base and the emitter, and we'll see how much R pi is. And now this R pi has a voltage across it, which we call VBE. Actually we call it V pi in bipolar devices. So we call that V pi. Okay, and remember the transistor is always a voltage dependent current source. So we have a current source here going to the emitter, and the value of this is now Gm times V pi. That makes sense, right? Because we said the change in the collector current is equal to Gm times the change in the base emitter voltage, and V pi is a small signal quantity representing only the changes in the base emitter voltage. Okay, so that's the simplest model that we can have for a bipolar device. What we know is that Gm is equal to IC over Vt. This capital IC is the current that exists inside the transistor before the signal comes in. So we have biased the transistor, we got some amount of current flowing through it, and based on that we can find the transconductance. And then R pi is simply beta times Gm, so that's beta over Gm, so that's beta Vt over IC. So you can see that if we know the room temperature, we know Vt. And if we know the bias current, the collector current of the device, before the signal comes in, we have these two, then we automatically have Gm and R pi, because beta is also known for the transistors. Okay, so we can see that this model is now clearly well defined. Once we know how much current we have in the device, for bias conditions before the signal comes in. But remember, we talked about the early effect, and we said if the collector-emitter voltage changes, so does the collector current. Right now, this doesn't predict that. It doesn't have any dependence of this current upon this voltage. So how do we model that? We're going to add a resistance we call RO between the collector and the emitter. Okay, so remember, this is not from the collector to ground, but between the collector and the emitter. And that resistance also has a value that can be obtained. So RO is how much? RO is given by the early voltage. When you buy a transistor, this early voltage is given to us, divided by the bias current in the collector, IC. So we see that the bias current of the device, meaning the current that exists in the device before a signal comes in, has a great effect on everything, right? In the output resistance of the device, transconductance of the device, and R pi. Okay, so based on what we have talked about so far, we can see why we bias transistors. We bias them for two purposes. Number one, to ensure they operate in the right region. For bipolar devices, it must be the forward active region. So the base emitter should be forward biased, the base collector should be reverse biased. Number two, we bias them so as to establish the right amounts for right values for the parameters of interest. For example, if I want to have a certain amount of transconductance, I have to choose a certain amount of bias current. If I want to have a certain output resistance, I have to choose a certain amount of bias current. So these two are the reasons for bias in transistors. So question number one in this homework will be, question number one, why do we bias transistors? Okay. We also have question number two for this homework. Question number two, what is the difference between large signal and small signal operation? Okay, so those are two questions for homework number one. All right, so based on these, now we are ready to go and look at bipolar circuits. I just wanted to mention one more point, and that's also critical, sometimes confusing, but absolutely critical. So let's change the color to blue. Okay, so the small signal model that I have shown here for the NPN transistor is exactly the same for the PNP transistor. So I'm going to write exactly the same for PNP transistors. Okay, when I say exactly, I mean literally exactly. There's no negotiation. It's the same exact model that can replace a PNP device in small signal analysis. Okay, so with these we can look at this general procedure. So we say procedure for analysis and design of amplifiers. And many other circuits, not just amplifiers, but in this course, in 115A, we've been dealing with amplifiers primarily. So, as you might remember from 115A, and as you might guess by now, first we want to create the right bias conditions for the transistors. So we say create proper biasing for transistors. We want to have the right region of operation, and we want to have the right values for the small signal parameters, GM, RO, RPi. Okay, once we do that, we add some stuff around the transistor so that this happens, some resistors here and there. And once we do that, now we are ready to analyze how the circuit behaves when a signal comes in. So, analyze the response to an input signal. And that means that we're going to use the small signal model. Small signal model. Now you may say, is it always true? Is it always true that an amplifier is guaranteed to operate in the small signal regime, meaning that the signals that are coming in create only small perturbations? No, that's not true. In fact, in 115B, we will see some cases where the circuit does have to take signals that are large, and it will do all sorts of interesting things with those signals. But for this review, we assume that the signals coming into the circuit are small enough that we can use the small signal model, this model. Okay. All right, so we will use these ideas to analyze three types of bipolar amplifiers. So let's go to bipolar amplifiers. And you have seen these in 115A, so we start with the common emitter stage. Then we go to the common base stage, and then we go to the emitter follower. Okay, so let's start with the common emitter stage. The common emitter stage, in its simplest form, consists of a single transistor with the emitter grounded. I call this Q1. There's a resistor here, which we call RC, and it goes to a power supply. So here's a battery, which we call VCC. And the way we recognize this as a common emitter stage is that the input signal goes to the base, right here, and the output signal comes out of the collector, right here. So for these amplifiers that we study, we're interested in three parameters. Number one, the voltage gain of the circuit. If I apply some 1 millivolt signal to the input, how large a signal do I get at the output? Number two, the input impedance of the circuit. So if I sit here and look this way, how much impedance do I see? And the output impedance of the circuit, meaning if I sit here and look this way, how much impedance do I see? All right, so those are the three parameters that we are interested in. Okay, so let's start with the voltage gain. So voltage gain, we call it AV. Now, generally, I would replace this transistor with the small signal model, and then write KVLs and KCLs and find V out over V in. That would be the small signal voltage gain. Remember that when we draw the small signal model of a circuit, we replace the devices with such models, but also all constant sources, all constant independent sources are set to 0. For example, this voltage source is constant and independent, so it's going to be set to 0. If you have a current source somewhere and that current source is constant and independent, again, that has to be set to 0. It becomes an open circuit. So remember that for small signal analysis. All right, so I could do this. So I could draw the small signal model of this guy. So let's do that. Here's how it goes. We have R pi, V pi, The emitter happens to be grounded, so we ground it here. Our input goes here, V in. Our dependent current source goes here, GM V pi. Let's not worry about the early effect for the moment. And the collector of the transistor goes to RC, and RC goes to the battery. The battery is set to 0 because it's an independent and constant voltage source. So when I set this to 0, it becomes an AC ground. So our resistor RC goes to AC ground. This is real ground. This is AC ground. And the output voltage is taken here. So what I notice is that V pi actually happens to be V in. V in is from here to ground. V pi is from here to ground, same voltage. And this current flows this way through RC, generating a voltage, which is this current times this resistance. But there's a negative sign because the current is going this way, not going that way. So then I can say V out is equal to minus GM RC times V in. Okay? And that means that AV is just minus GM times RC. So we articulate this as follows. We say the voltage gain of a simple common emitter stage is given by minus GM of the transistor multiplied by the total resistance that we see from the collector of the device to AC ground or real ground, the total resistance. In this case, because the early effect is neglected, what if we sit here, all we see is RC to ground, right? This RC, we don't see anything else. All right, so this brings us to problem number 3 of the homework. So number 3, find AV if the early effect is not negligible. All right, should be pretty straightforward. Okay, so we found the voltage gain of the circuit. Let's go ahead and find this input impedance. The input impedance can be obtained in the general case by connecting a voltage source from here to ground. You can call it V in or Vx, and find the current that flows through that voltage source, divide that voltage by that current, that gives us the input resistance. Again, remember, the input resistance is a small signal quantity, so it has to be, has to be obtained from this circuit, not from the large signal model. Okay, so this is pretty easy because if I just put my voltage source like this, call it anything you want, we see that this voltage source sees exactly R pi in parallel with it and nothing else. So then R in is just R pi. Right? Okay, and how about the output resistance? The output resistance can be obtained by applying a voltage source from here to AC ground, and again trying to find the current that we deliver. Now when we do that, we have to set all independent sources to 0. So let me try to do that for R out. We draw the model again. Here's what we have. Here's R pi. And I come in with a voltage source here. We call this Vx. This is Ix. Vx over Ix represents the output resistance, provided that all independent sources in the circuit are set to 0. So, including this guy Vn, the input voltage to the circuit has to be set to 0. That means that the voltage source is replaced by a short circuit. So, this will be shorted to ground, which means V pi is now 0, which means this current source is 0. A 0 current source becomes an open circuit, so that's gone. All that's left over is RC. So R out comes out to be RC. If the early effect is neglected. So what if the early effect is not neglected? That should be easy enough, right? I'll leave it for you to figure out. Okay, So this was a quick analysis of the common emitter stage. Let's go on to a variant of the common emitter stage that's extremely important, and that's what we call a degenerated common emitter stage. So we're going to go to the next page and look at the degenerated common emitter stage. Okay, so degenerated CE stage. All right, so the idea is that we still have a common emitter stage as usual. The input goes to the base, the output comes out of the collector. That's the definition of a common emitter stage. Some sort of resistance here to the positive supply, VCC. But the emitter is not grounded. The emitter goes through some impedance, resistance, maybe resistance and capacitance, whatever you want, to ground. So for example, we have a resistor here. We call this RE. This degeneration improves the performance of the circuit in a number of perspectives. We saw in 115A that the overall voltage gain of the circuit becomes less dependent upon, for example, temperature or bias current, because this RE plays a major role in the voltage gain, as we will see in a second. All right, for this analysis, we'll assume that the early effect is negligible, so that the analysis is simpler. We include this early effect for degenerated circuits only in graduate courses. So in 115B even, we will not worry about this. Okay, so it turns out that the voltage gain of the circuit is given by, as we found in 115A, minus RC, the total resistance tied between the collector and AC ground. So here is just RC that goes to AC ground. And the denominator, we have 1 over Gm of the transistor, 1 over Gm, plus the degeneration resistance, Re. Okay? So of course, if Re is 0, this goes away, this Gm comes up, we reduce to the undegenerated common emitter stage. So that's to be expected. Now, why is this a big deal? Why is this degeneration important? Well, what we see is that if Re happens to be much greater than 1 over Gm, then this goes away. And what we have is the voltage gain as the ratio of two resistors. And the ratio of two resistors, especially in integrated circuits, in microchips, can be controlled very well with 0.1% error. So this ratio is very accurate. And in fact, if these two resistors together change with temperature, for example, the ratio still doesn't change. The ratio is still accurate. Whereas previously, if we didn't have Re and Gm was IC over Vt, remember Vt has temperature in it, the gain would be temperature dependent. So when you test the circuit in Saudi Arabia with a very high temperature, or in Finland with a very low temperature, you're going to get very different gains. So this Re helps stabilize the gain against temperature and process variations. Okay, all right. How about the input resistance? The input resistance of the circuit was obtained in 115A as follows. We have R pi as before, but not just R pi. To that we have to add Re, but multiplied by a certain factor. And that factor was beta plus 1 times Re. So what's interesting is that R pi and Re are not in series. It's much more complicated because we have a dependent current source here. So what this circuit does is it takes the degeneration resistance and reflects it to the base, so to speak, with a magnifying factor of beta plus 1. So the resistance that we see here is this raised or multiplied by beta plus 1 and then added to R pi. So anything that we have connected from emitter to ground is multiplied by beta plus 1 when we see it from the base terminal. All right, and finally R out. the output resistance of the circuit. If we sit here and look, well, all we see is RC to AC ground. We don't see anything looking down because there's no RO. So R out is just RC. Okay? All right, this brings us to problem number 4. Let's see. Okay, now I'll talk about problem number 4 after the common base stage. Let's move on to the common base stage. Okay, so again, we have a single transistor, but this time the input does not go to the base, it goes to the emitter. So here's how it goes. You can draw the transistor either way, this way or the other way. You can draw it this way or that way, mirror it if you want. So here's a certain bias voltage connected to the base, and the input is applied to the emitter. The output is taken from the collector. And there's a resistance to VCC, just like before.